Okay, so good afternoon, everyone. Welcome to this special workshop organized by the Hong Kong Young Academy of Sciences and the Hong Kong Young Industrialists Council and the Innovation and Technology Commission. So today I'm the chair. I will moderate the entire workshop. My name is Zijian. I'm a professor at the Hong Kong Polytechnic University. So today we will have two speakers. But before the speakers, I would like to introduce our two presidents of the societies. One is Professor Anderson Sum, president of the Hong Kong Young Academy of Sciences. And then is Mr. Paul Tai, president of the Hong Kong Young Industrialists Council. So first I would like to introduce Anderson. So Professor Anderson Sum, he is a professor at the University of Hong Kong. He's an expert in biomedical devices. So let's welcome Professor Sum to give us a very brief opening speech. Anderson, please.
Thank you, Zijian. Mr. Paul Tai, President of the Hong Kong Young Industrialists Council, Shih-Chi, Mingxin, Zijian, HUANG members, fellow YASHK members, students, and everyone, good afternoon. The Hong Kong Young Academy of Sciences is honored to cooperate with the Hong Kong Young Industrialists Council, HKYIC, to organize the Industry Workshop 2022, Advanced Manufacturing Technology. This year marks the 25th anniversary of the establishment of the Hong Kong Special Administrative Region. Looking back on the past 25 years, there are some successful examples of scientific research transformation in Hong Kong. For example, the non-invasive prenatal test technology developed by Professor Dennis Low has been done and transformed in Hong Kong. It is now used in more than 90 countries, benefiting 7 billion pregnant women every year. It can be seen that the industrialization of scientific research in Hong Kong can have a great impact. Innovation and technology is perceived to be a key engine, driving the diversification of Hong Kong's economy. The Hong Kong government has been taking a proactive approach to enhancing the INT ecosystem of Hong Kong, enabling high value added as well as creative and technology intensive new industries to lead the city's economy to take off again by fostering reindustrialization. In 2018, YASHK was established. We currently have 53 young scientists as our members. We do not only promote the science and technology education in Hong Kong and foster the development of the city to be an eminent international science, technology, and innovation center, but also actively collaborate with industrial and commercial sectors to strengthen the conversion applications of scientific research achievements. We actively cooperate with industries to promote the translation and application of scientific research findings. This is the third industry workshop. We have jointly organized with HKYIC to introduce the latest technological developments and scientific discoveries to the industries. We have conducted a workshop on energy storage and AI and robotics. This time we are going to focus on advanced manufacturing technology. I am thrilled to be here to learn from our YASHK fellow member and ready to know more about their technologies, just like you. I hope all of you will enjoy the workshop. Thank you very much.
Thank you very much, Anderson. Now let me please invite Mr. Paul Tai. Paul, would you please give us also an opening speech, please? Thank you.
Thank you. Anderson, Professor Zhang, Professor Chen, Professor Huang, friends and ladies and gentlemen. You can see I'm actually now outdoors, so that's why I have to wear the mask. I hope you don't mind. It gives me great pleasure to join you all here today for the YASH and YIC Industry Workshops 2022 on behalf of the Hong Kong Young Industrialists Council. I'm most honored to have this opportunity to join hands with YASHK again. In the last 2 years, we have a lot of programs that Anderson's already shared with you. We already have done 3, very exciting. And I think this is very important. We all have the same goal and shared goal that research and development are essential for Hong Kong industrial development. We Hong Kong YIC are always in full support of the local R&D development and dedicated to strengthening the coordination amongst the government, industry, academia, and research sectors so as to build Hong Kong into an international innovation and technology hub. So last but not least, I wish all of you enjoy the following presentation and have a fruitful afternoon. Thank you very much.
Thank you very much, Paul. So I think after this 2 opening speech, we would like to have a virtual group picture. So please, for those who have and is convenient to open up your cameras, please do. So you can turn on the camera and we'll say a hi or a thumbs up. So and Ada will take a picture for us, please. Okay, so thank you, Ada. Right, now I think we'll start our presentation session. So let me talk about the rundown very briefly before the presentation. So basically, we are going to have 2 25 minutes presentation, and then we'll have a 30-minute discussion and Q&A session following the presentation. So please put down your questions. You can type your question in the chat box in the Zoom, and then I'm going to read out the questions. And if the questions are very similar, I probably will combine some of the questions together and raise the questions at the end. Okay, so let me introduce the first speaker. The first speaker is Professor Chen Shih-Chi from Chinese University of Hong Kong. So Shih-Chi is a professor in the Department of Mechanical and Automation Engineering. So he received his bachelor degree, Bachelor of Science in Mechanical Engineering from the National Tsinghua University in Taiwan in 1999. And then his master and PhD degree in Mechanical Engineering from MIT in the US in 2003 and 2007, respectively. Afterwards, he worked as a postdoc fellow in Harvard University in the medical school. And then later on, he had worked in the company for a short while and then moved to come to Hong Kong and started his independent career. Shih-Chi is well known for his leading work in this advanced manufacturing. Today he's going to give us a talk in this area. So the title of the talk is Recent Advances in Micro-Additive Manufacturing and 3D Nanofabrication. Shih-Chi, would you please share your screen and start your talk? Thank you.
Sure. Can you see the screen?
Yes, yes.
Okay.
Very clear.
So I would first like to thank Zijian for the introduction and welcome everybody to the seminar this afternoon. I'll take the opportunity to share some of the research progress in my lab and talk about the area of micro-additive manufacturing and 3D nanofabrication. So before I start, I'll briefly introduce my lab. Our lab is focused on generating the scientific knowledge in designing ultra-fast imaging systems, precision machines, and laser fabrication systems. And today we'll be focusing on laser fabrication systems. Okay, so 3D printing technology has revolutionized the engineering industry in the past 2 decades. Although there have been a lot of rapid progress and development in the field, there are still great challenges, especially lying in the area of micro-additive manufacturing. Although there are methods that can create sub 200 nanometer features in 3 dimensions, the speed is prohibitively slow and the cost is extremely high. I will give an example. If you want to print a cubic centimeter size object with 200 nanometer resolution, it would typically take 1 or 2 months and costing around hundreds of thousands of dollars. And you know that is not practical for any industrial application. So what if we were able to print sub 100 nanometer resolution at a scale and speed, just like a regular 3D printer as shown on the right, and at the same cost, and in terms of material, we can use all kinds of material, then we believe the engineering design process will be revolutionized again. And today I'll share with you some of our work that shed light on this ultimate goal. So to begin, I'll introduce the most precise 3D printing process, two-photon polymerization. So the technology was first introduced in the late 90s, and everybody learns about it in 2001 by the seminal work from Kawada's group in Japan. And now everybody knows this nano-ox. About a few years later, the technology was commercialized by a German company called Nanoscribe. And today, most universities and research institutions will have a unit from Nanoscribe to print, various micro to nanoscale devices for experimental verification or scientific research. So on the upper right corner shows a microneedle array for drug delivery application. Bottom right corner shows micro lens array for any imaging systems. So although TPP is a photopolymerization process, you can actually extend the material to other areas and different materials through different methods. On the left shows if you print TPP as a template, by combining with electroplating, you can create pure metallic structures. Many people also mix nanoparticles with photoresin to make functional devices directly. In this example on the right shows a piezoelectric devices printed directly. If you mix magnetic particles, then you can create micro robots maneuverable in body or in vivo, which is a fast growing field. Another big area of application is to directly print biocompatible and biodegradable tissue scaffolds. And all these were limited by the high cost and slow printing speed. So if you wonder what TPP can do in terms of high throughput fabrication, in fact, in comparison with e-beam lithography or very expensive diamond turning, TPP can be used to make metallic molds. So you can start with fabricating complex, 2D or 3D structures. Then you electroplate and make a metallic mold. Of course, the polarity is inversed. And then you can use it with injection molding to make various parts. And this will be one low-cost way to fast develop prototypes. Of course, this needs to be established on the fact that TPP is a low-cost and efficient process. Okay. So next, let me briefly talk about the basic principle of two-photon polymerization. This is a process enabled by a nonlinear two-photon absorption process enabled by the ultra high peak power femtosecond laser. So due to the extreme high power within the focal point, 2 photons will be absorbed by an electron as shown in the Jablonski diagram on the left. It goes to higher energy states and release free radicals that generates the photopolymerization process. In comparison with a conventional stereolithography process, 2-photon process has depth discrimination. In other words, it only polymerize material within the focal point that's much smaller than a size of 1 cubic micron. And also is very sensitive to a polymerization threshold. So in other words, if you fine control the laser power, you can write structures much smaller than the diffraction limit. And that's why much smaller features than the wavelength of light can be created. So this is what's been done in the past. So people pair the femtosecond laser with a pair of scanning mirrors. As a result, by raster scanning the laser focus, voxels can be created in a line-by-line, layer-by-layer fashion. So when one layer is completed, the laser is moved to the second layer by a specimen stage or piezoelectric objective scanner to complete the 3D fabrication process. And this is very slow. So this video taken from Nanoscribe illustrates this process. So you can see to print an aircraft as shown here, laser is raster scan horizontally as the fax axis, vertically as the secondary slow axis, and then it moves to the next plane. Although this process seems to be fast here, it is extremely slow because you know that the entire thing is smaller than the diameter of your hair. And let me talk about more process. So during the printing process, the objective lens is immersed in the photoresin, which is in liquid form, which has a refractive index of 1.5. So in order to ensure high resolution, a matching index objective lens is used. So it's typically an oil immersion lens. So after fabrication, you take out the sample and develop it, and you can visualize the result in high resolution electron microscope, as shown here just now. Okay. So to make it practical, you know, not just me, a lot of people have been trying to speed up the process. And one straight solution is to use multiple laser foci. So you can split the laser focus, for example, by using micro lens arrays or diffractive optical elements. But that usually has a fixed focus pattern, so you can only write periodic structures. And also the focus quality is compromised. So we want to address the issue by a different approach. In other words, to efficiently and quickly manipulate the laser wavefront. So first, we surveyed different special light modulators. You know, there's liquid crystal special light modulators, deformable mirrors. In the end, we decided to use a very unique device, which is the digital micro mirror device. This device, actually, everybody here online have seen it in the past because it is the very chip used in every projector in every movie theater, made by Texas Instruments. So DMD, as a result, is very high resolution nowadays. It's 4K. It's also very high speed, up to 32 kilohertz. Each mirror is a binary display. It only has plus minus or 12-degree position. So when we combine a DMD with the femtosecond laser, you know, it becomes an ultra-fast scanner. So what we do here is we design specific holograms. And because DMD is binary, so we design binary holograms and place it on the DMD. Then the femtosecond laser is introduced to the DMD as a reference beam. So as a result, the design hologram is recreated here. So some people may wonder how come this was not done in the past. And the reason is for the longest time, DMD is considered not comparable with the femtosecond laser because the pixels on the DMD are too small, which causes dispersion. And we address the issue with this dispersion compensation design as shown in the US patent here. And as a result, when we measure the pulse width after the DMD, it shows very narrow pulse width and the diffraction effect has been entirely removed. So fortunately, the design of digital hologram theory is derived already in the 1970s. So whatever wavefront information we want to create, we just convert them from the analog equation form into digital form through the inequality shown here. So we substitute to this equation, and if it satisfies the inequality, and we have the value of 1, and otherwise 0. So everything turns into a black and white picture on the DMD as shown on the right, and on the left shows the recreated wavefront. So next, I'll talk about how to use the hologram to perform focus scanning. To perform axial scanning, we can just design a spherical wavefront, which bends a planar wavefront into spherical shape with a specific focal length. So the left term on the inequality is so-called the tilted face term, so which represents the special frequency of a fringe pattern display on the DMD. So by varying the special frequency, we can then alter or move the focus laterally. So here we show a simulation of varying DMD patterns. As you can see, as the special frequency moves, the focal point would move as predicted. So based on our calculation under a 40x objective lens, we can fast control the focal point in the axial direction for about 500 microns and laterally for about 200 microns with accuracy and minimum step size of about 100 nanometers, which is sufficient for our target application. So then we briefly talk about how holograms are synthesized. So we can design the lateral and axial position and superpose them directly. Once we design one focus, we can design all other different focus and superpose them to form a single hologram. We can even design wavefront correction information and add it to the phase term here. And as shown in this video here, 4 laser foci are generated, and as you can see, each of the laser focus can be individually controlled to move within the same workspace. And they are actually making 4 different structures, but you only see 2 here because the other 2 are in a different depth. Okay, so here we briefly compare the difference between the conventional process and our random access scanning process using this 2D home. So in raster scanning conventional process, laser has to be scanned layer by layer. So even if you have empty spots, you have to scan through them and you just turn off the shuttle, okay? In our process shown on the right, each color represents one exposure. So we can expose multiple points simultaneously. We can build these pillars through a different beam mode, for example, the bezel beam. So as a result, these empty spaces, we don't really need to go there. And as based on this principle, we increase the fabrication speed by around 2 orders of magnitude, comparing with point scanning process. So in 2018, we received the R&D 100 award for developing this prototype. And it is simultaneously a 2-photon imaging system that people use to study brain and neuron activities in vivo. And you can see some of the high resolution structures printed in our earlier system in 2019. You can see individual voxels overlapped in this high resolution SEM images. In the recent 1 or 2 years, we further enhanced the performance of the system by using a regenerative laser amplifier. And nowadays, we can use up to 2,000 laser foci, achieving a 2 million voxel per second writing speed and breaking the record of resolution down to 90 nanometers. So to quickly summarize, we use a digital micromirror device to perform high-speed multi-focus scanning, and each focus is individually programmable and can perform random access scanning. In fact, each focus can also carry different laser power, so they achieve grayscale control. Very, very capable system to create 3-dimensional structures. But we are not satisfied with the performance. To further enhance the speed, we come up with another idea. So instead of splitting the laser focus, we were wondering whether we can focus the laser instead of a point, but into a thin light sheet, which contains millions of points. And on the light sheet, is it possible that we create patterns? And the answer is, of course, yes. And to introduce the principle, let's briefly talk about the basic properties of femtosecond laser. As I mentioned, femtosecond laser refers to a laser, a pulse laser with very narrow pulse width of 100 femtosecond. If you consider the time bandwidth product as a constant, you will realize that femtosecond laser contains many different colors, unlike continuous wave laser. So the bandwidth is wide. And that's why DMD would cause dispersion in the first holography technique. We want to avoid this. In this technique, the so-called temporal focusing technique, we actually exploit and take advantage of the dispersion effect. So the femtosecond laser is brought to an optical grating. As a result, different color spectrums are dispersed. And when dispersion occurs, the peak power laser The laser peak power is lower and cannot perform multi-photon absorption or excitation effect. Then all these dispersed spectrons are recombined and only at the focal region they are overlapping. As a result, it forms a thin light sheet at the focal region, and right after the focal region, light becomes dispersed again. Okay, so this slide shows an image comparing with the conventional point scanning or so-called special focusing idea. So energy of a laser system is focused to this point, and by raster scanning the point, material is processed. But along the light path, the pulse width remains a constant. In a temporal focusing system, we do not focus the laser beam. The laser beam diameter is adjusted to be equivalent to the processing area. As you can see along the light path, the pulse width is varying instead, and only at the focal plane, the pulse width is narrow and can have multi-photon effect. This idea was actually not invented by our group, but some of the microscopists in 2005. In order to use this for fabrication, we have to generate specific patterns on the light sheet, right, in order to perform fabrication. So that's where our contribution came in. We replaced the optical grating with a digital micromirror device. As I said, DMD is a blaze grating with an angle of 12 degrees. So by selecting the proper diffraction order in an experiment, the -5th order diffraction, we can achieve high laser efficiency, around 50%, and implemented temporal focusing. So as a result, the DMD surface and the work plane is in conjugation. So whichever pattern displayed on the DMD will be displayed here. And next, by axially moving the focal or light sheet around, and by changing the pattern accordingly, we can create arbitrary structures of high speed. So this slide shows a simulation of the intensity profile of the light sheet. You can see it has a thickness around a few microns. It's extremely flat. So by just moving the light sheet around, we can drill flat bottom holes, which reaches a 50 nanometer surface roughness on nickel target. So we apply this to two-photon polymerization in working with Lawrence Livermore National Laboratory since 2015, where they developed custom designed photoresins for us to deal with a high-power laser regenerative amplifier. So you can see using the system here, each exposure defines a layer, but you're actually seeing a slow motion because every second we can define roughly 100 to 1,000 layers. So this further pushes the fabrication rate of our previous system by 1 order of magnitude. Okay, you take out the printed part, it's transparent in optical microscope, but in electron microscope, you can see fine log pile structures being created. You can also see these artifact or defect caused by a dead DMD pixel. Another advantage of this system is the voxel aspect ratio is not conventional Gaussian beam aspect ratio 1:3. Instead, it's 1 to 1.25. And this is because the voxel or resolution of a temporal focusing system is not determined just by the Rayleigh's criteria. In other words, wavelength and numerical aperture. It is also simultaneously determined by the pulse width. The narrower the pulse, the thinner the light sheet. So by carefully selecting the spectrum in combination with the numerical aperture and wavelength, we can tune the aspect ratio of the voxel in a temporal focusing system, as shown here. So from a 1:3 ratio, we make it a 1 to 1.5 ratio, which is resulting in superior mechanical property of the printed structures. So by carefully studying the laser dosage relationship with structural integrity, we can create all kinds of 3-dimensional structures. For example, this column has a diameter roughly equivalent to your hair and various large-scale structure that cannot be created in the past. And also the cost is reduced by around 95%, and the throughput is now roughly 100 cubic millimeter per hour versus originally 0.1 cubic millimeter per hour. Okay. As a result, this work was published in the Science magazine. And if you see this work in comparison with all other works, you can see most other works, they're playing with the trade-off between speed and resolution. So high resolution, low speed, high throughput, low resolution. But we fundamentally address the issue and simultaneously achieve high speed, high resolution, and low cost through this work. Okay, but there is a limit on the resolution we can achieve, roughly 100 nanometers. On the other hand, many metastructures, especially in visible light applications predicted by scientists, require features below 50 nanometers. And that's some area that we are working on right now. And with limited time, I can briefly talk about the idea. Essentially, we use a hydrogel as substrate because hydrogel is swellable. So we print structure on the hydrogel in expanded states using our light sheet system. And after that, we follow by a material deposition process. And lastly, we can shrink the hydrogel by putting it into the hydrochloric acid. As a result, we can create all these freestanding three-dimensional metastructures of 20 nanometer resolution. And you can see the resolution test to be less than 50 nanometers. We also try with different materials. The materials now include metals, metal alloys, metal oxides, semiconductors, or even biomaterials. And since this work is currently under review, I would limit the discussion here. So if you're interested in learning more, welcome to approach me privately. So now I would like to summarize the work I presented today. So based on digital micromirror device and ultra-fast lasers, we have introduced new 3D printing systems that achieve substantially increased speed without compromising the resolution. The light sheet system further improved the speed by an order of magnitude and reducing the cost. And lastly, we talk about a swellable hydrogel platform in creating three-dimensional metastructures. So with that, I will conclude my seminar. And of course, everything you see here was not done by myself, but by my students and my team. Thank you.
Thank you very much, Shih-Chi. Now, let me introduce the second speaker. Again, I would like to emphasize that if you have a question, please put down your question in the chat box, and I'll ask that after the second speaker finish his talk. So second speaker, Professor Mingxin Huang. Professor Huang is now a professor at the University of Hong Kong. He received his Bachelor of Engineering and Master of Science in Mechanics from Shanghai Jiao Tong University in 2002 and 2004, respectively. And then he received his PhD in Material Science in 2004 from Delft University of Technology in the Netherlands. After finishing his PhD, then he worked as a research engineer in a company, and then he came to Hong Kong in 2010. So he's known for his expertise in all this engineering materials, stainless steel, for example, and alloys. So today he is going to give a talk on anti-COVID-19 stainless steel. Mingxin, please.
Okay, thank you, Zijian, for very kind introduction. So good afternoon, everyone. Thank you for joining the seminar. Today, I would like to introduce our latest results on a special, very special stainless steel that can actually kill this COVID, this SARS, this virus, COVID-19. So the idea for this one is during this pandemic, we like to invent something which can be useful. So this is a team together. We work with the medical school in Hong Kong U. So my team here together with the PhD student Liu Litao here, and with the Professor Leo Pun at the medical school, and Dr. Alex Chan also from the medical school. So this funding was, this project was funded by RGC and ITF project. But originally this project was aiming to develop a stainless steel for this influenza, for influenza H1N1 virus. That was in the project start a few years ago before the pandemic. So when the pandemic starts in 2020, so we switched our focus. So because at the beginning we thought if we are able to kill influenza, we might be able to inactivate the this COVID-19 virus. So that's why we switch, and with the help of the medical school, using their laboratory facilities, then we can do the testing. Okay, that's the idea. So it's a brief introduction about the basically the use of the stainless steel. Basically, is a daily, is a daily product you can see everywhere. Basically, in the MTR, in the metro system, in the your door knobs and the toilet buttons and the leaf buttons. They are grip and cost per bed. I mean, really, you see many applications using stainless steel. So of course, this COVID that has one of the form for transmission, that's surface contact. So our stainless steel here is talking about surface contamination, not this by through airborne transmission. So because one basically, if you have a cough droplets, you may have a lot of these droplets containing a virus. And this virus, if they stop in the normal stainless steel, that can last for 2 or 3 days. This virus, you still can detect live virus, which is transmissible. So the idea is that to prevent just for this surface contamination for the transmission. So if you remember the really at the very beginning of the pandemics, you see many people when they go into the lift, they will use their key or the tissue to push the lift buttons. And actually, we are actually seeing that, and there's an inspiration saying, why not? If we are able to develop a stainless steel, but not using coating, because if you're using coating on the surface for the antivirus, with the time this coating will disappear. So the idea is that if we are able to develop a stainless steel, which can be used for a permanent antivirus properties. So that means you don't need coating. So the stainless steel itself must has this antivirus properties. So that's the driving force behind why we try to develop this new stainless steel with these antivirus properties. So after we did this, we make this stainless steel with a special chemical composition. If you go to the literature, you can see that actually antibacterial stainless steel has been developed over there for 20 years or more than 20 years. But that's antibacterial. So antivirus is different because bacteria and virus are very different species. So in this case, the inactivation mechanism is different. So there's no really, we can search for the literature. So there's no really stainless steel can talk about the antivirus. Okay, stainless steel that can be used for antibacterial available in the market, but stainless steel that can be used for antivirus are not available in the market. So basically it's no. So that's why we do it. So we develop differences. So this is an experimental results. And this is a sample. How we do the testing is basically the sample. We make a droplet. This is a virus content droplets. And then we drop onto the surface. Okay, just to simulate the contamination. When you're speaking, when you're coughing, you have the droplets dropping on the surface. Okay, so in this case, what you can see, is we wait for a given period of time from 1 hour to 48 hours. And then we try to measure how many the percentage of virus are still viable. That means it's still live virus. Okay, so the very beginning is 0 time. Okay, 0 time. Look at this 316L stainless steel. This is a very conventional stainless steel. This is a conventional stainless steel. Here's a pointer. So for the conventional stainless steel, you can see that actually after 48 hours or 24 hours, you still have a live virus on the surface, okay? Not mentioned for a few hours. And this is the conventional stainless steel. And we also try, because copper and silver are known for antibacterial properties. Okay, so antibacterial is very different to antivirus. So in this case, we also try a pure copper and pure silver. You will see that pure silver is surprisingly, at the very beginning, we thought pure silver might be also to use as an antivirus because pure silver is good for antibacterial, but our results shows that this silver is not much better than stainless steel. So in other words, silver itself is not working for antivirus properties. Then we see pure copper. This is the pure copper. Now pure copper is the best. Okay, so we do the testing. We see pure copper even under 1 hour or 3 hours later, pure copper shows the best antivirus properties. So it means basically you have 90.99% of the virus are killed. So even if 6 hours later, you cannot detect any virus. Okay, so pure copper is the best. So then we using a powder metallurgy technology to make stainless steel. SS stands for stainless steel, that containing different silver contents and all silver different copper contents. So for stainless steel containing silver contents, this blue line and this light blue here. So you see this stainless steel containing silver does not have this antivirus properties. And then we check one represent 1%, 1 weight percent of copper, 5 weight percent of copper, 10% of copper, and 20% of copper. So you can see that this stainless steel with different copper content, you see the properties is different. Okay, look at this 20% copper, which is the best in terms of the antivirus properties for the stainless steel. And this 10% copper also has these properties. Let's say after 24 hours, there's no more live virus can be detected. So if taking for potential applications, if you're taking 20% copper in the stainless steel, you will see that after this one is almost about 99.9% of the virus will kill within 3 hours. So the amount of virus was reduced on the surface, then the chance, the possibility of getting, let's say, affected by this virus is to be lower. Okay, so less virus on the surface, the probability for infection will be lower. So in this case, we consider 20% of stainless steel. Stainless steel with 20% copper, we have a very good application potentials for, let's say, leaf buttons. Well, because usually you clean the leaf buttons every 2 or 3 hours. That means using our stainless steel, in this case, even you don't do the cleaning, within 3 hours, the amount of virus on the surface is very low already. Okay, so this can help to reduce the risk of this transmission. Okay, so we also check the ability for anti-H1N1. Okay, so we can see that our 20% of stainless steel with 20% copper also show a good anti-H1N1 virus properties. Of course, once again, copper is the best, but silver, again, silver is just the same as the normal stainless steel. So means silver is only working, it's working very good for antibacterial, but it's not working for antivirus. But this anti-copper, the copper works for both. But if we use pure copper is more expensive, right? So stainless steel can lower the cost. That's why we should still do stainless steel. In addition, the appearance of stainless steel is different. For any product, you like a stainless steel property, like the hardness, the strength, the wear resistance, the cost, and in this case, stainless steel always better than the copper. Okay, so for like leaf buttons, you don't use pure copper to make leaf buttons, but you use stainless steel, or the hand also other applications where you have stainless steel, but you don't use pure coppers. And in addition to the antivirus properties, we also check our antibacterial properties. So clearly, pure copper is also very good. If you don't see any bacteria here, okay? So this is the stainless steel. After 24 hours, you see a lot of bacteria. So it means normal stainless steel doesn't have this antibacterial property, also does not have the antivirus properties. But for pure copper, you have the antivirus property. You also have antibacterial properties. So for our materials with 10% or 20% copper, you also have excellent antibacterial properties. So in short, this stainless steel with 20% has the best antivirus and also antibacterial properties. Okay. The reason why is our stainless steel can have this antibacterial properties. So basically, if you look at the microstructure, so it's 10% of the copper, you will see that all these white dots are copper precipitates. Okay. Now this color here represents the copper. So you see also the X-ray. These are EDX. For the EDX, you also see this copper here. So clearly, we have this copper precipitation in this stainless steel. In the normal stainless steel, you do not have these copper precipitations. Okay. For higher copper contents, we are going to see more of this copper precipitation. So basically, we change the microstructure of the steel. And we also check the concentration. We check the concentration of the copper ions. Okay. So we expect that because of the copper ion release, and this copper ion is kind of reacts with the virus or the bacteria, that leads to the death of the bacteria or the inactivation of the virus. You can see that for pure copper, with a few hours later, the copper concentration is very high because you are pure copper itself, okay? But then if you have a lower copper content, 1% copper, 5% copper, you see the copper concentration is low. So with this 10%, 20% copper, you see, which is reaching quickly, within a very quick short time, reaching very similar to pure copper properties. So in this case, so that is explaining why a higher copper content can be a better antibacterial or antivirus stainless steel. We also check similar for this silver. You will see the values here is 20% ppm. Silver ions are very low, so 0.2. That could be also one of the reasons why the pure silver does not have this antivirus or antibacterial properties. So basically what we are doing, we try to make a demonstration whether or not our steel, our stainless steel can be used in a daily life product, like leaf buttons or in other applications. So we make the 2 leaf buttons using our stainless steel based on a powder metallurgy technique. Okay, we can also do casting. We can also do a conventional casting. To make this one, but conventional casting may have some technical challenges to be solved. But we are working on that now to solve the technical challenging if we're using conventional casting to containing such high copper content. But if we use powder metallurgy, it's quite easy. And powder metallurgy is a well-established technology actually to be can be available easily. So by powder metallurgy or sintering, now we can make these products, and which we already can be already done. So we have a patent applied already, and this patent was awarded a silver medal in this Geneva invention, and we also published this one in a scientific journal. And actually is also very interesting. It has been when we have this press conference. Overseas in companies, many companies are actually contacting Hong Kong U for potential applications using, and even also we also have interviews at BBC, and then that's really showing interest. And we also discussing with some of the companies at this moment to see if we can license the patents for them to make a daily products using, using stainless steel. So that's, I would like to summarize that we have invented a new stainless steel containing a high copper content that can kill viruses, including this COVID-19 and also influenza virus and also bacteria. And then these products can be made using existing industrial facilities, and then with a low cost, which can really I hope that we can make it into a daily product. Thank you very much.
Thank you very much, Mingxin. So I think now we enter the discussion session. So I already received quite a few questions. So please, if you have questions, please post them out as well. Okay, so I think Shih-Chi is with me now. So I will first ask questions to Shih-Chi, and then I'll probably swap back and forth. Now, the first question to Shih-Chi is, Professor Chen, how small can the item be printed by your 3D printer? And what kinds of industries are eager to use these items or parts to replace anything existing? So can you give this more general question?
I think the standard two-photon lithography technique has a resolution around 100 to 200 nanometers, so they can be used to create optical devices, gratings, and our new technique can further reduce the size to below 100 nanometers. So how to use the resolution is still to be explored, because fabricating these things of the resolution in 3 dimensions has never been realized in the past. So I give examples of, turning TPP printed structures into metallic molds. So that would be a way to utilize them to make, for example, cell phone lenses, miniaturized spectrometers, portable ones. So those would require components to be printed through our technique. But there are also other applications like, tissue scaffolds. So those are the bio or medical applications. With cost reduction, they can be potentially used in all kinds of fields, just like regular 3D printers. Yeah.
Okay, so following that question, there's one specific question about this meta surface. So I think the question was written down in Chinese, but then I translate to English, is that according to some reports previously, that your nano 3D print, I believe, can also print a metal surface for this application. Can you do that, or how did you do that? Is it appropriate for making some maybe military type of applications?
Well, yes. So I guess meta surface or meta structures are a broad term describing a wide range of optical and mechanical structures that possess properties that are not natural. So making things invisible is one, like invisible cloak is one possible application. So if you apply that structure into aircraft, you can make them invisible for visible light range. So that's possible. So, different frequency ranges require different scales of structures. And of course, you can also design structures that covers a broad frequency range. And I think all of them demands very fine structures to be made that beyond the current manufacturing capability. So that's why these works are important for the future perspective.
Right. Yeah, I think this is indeed there are quite a lot of possibility because it's a manufacturing tool, right? So in principle, the application can be very, very wide. Another question, I think it even looks further since the AI industry is also developing rapidly. How many years after or do you presume that AI can help us to design and making these 3D products that are more cost effective and less time costly?
I think it's already helping. So a lot of manufacturing industries are already using AI in optimizing their protocols, all kinds of process. For example, even the semiconductor industry, TSMC in Taiwan is implementing AI in all their processing steps. For 3D printing, AI can also help optimizing the trajectory in the design process, choosing materials. So, and I think people are continuing, growing the adoption of AI techniques. Yeah.
Okay. So I will pause a little bit here and switch it to Huang, Professor Huang, and I'll come back to Shih-Chi later. So Mingxin, you talk about a lot of this COVID or anti-COVID-19 one, and I think there are some questions related to the general versatility of the technology, right? So number one question is it also anti, Omicron or other type of COVID-19 variants? That's number one. Another one is does it also can kill influenza or normal like a cold viruses? Can you comment on that?
Yeah. So for influenza, we did already H1N1. That's is quite active, so there's no problem. We can inactivate. We can kill the influenza. For the Omicron, we just recently, but not yet published, and in the data. And recently, the medical school is helping us to do a testing. The preliminary results are also positive. That means our stainless steel can also, especially 20% copper stainless steel, can also kill this Omicron virus. Because for us, it's a kind of a mechanical or physical killing mechanism. It's a physical killing mechanism. It's different to the drugs. So in a way, for us, it should be quite a broad applications. So, but we need to do more testing for other types of viruses. But at this moment, the virus we test, this is working properly. Yeah.
Right. Okay. So another question is, other than copper, is there any other metal or mineral that can also perform similar functions?
Yes, it's a very good question. At the beginning, we thought silver is very good. Silver, as in the ancient Chinese, saying silver is good for let's say healthy, for killing this bacteria. Okay, we thought silver maybe also good for killing the virus. Silver is very good in killing bacteria, but surprisingly, after our experiment, we found that silver is not working. But for other metals, we haven't tried many, but zinc has been reported good for killing bacteria. But there's really no one report, I think, as far as I know, killing virus. So at this moment, we are trying copper, we have tried silver. In this moment, it looks copper is working very properly, but not silver. But other metals we haven't tried, but that could be there, but we just don't know yet. Yeah.
Right. I think come back to this material issue. I also would like to know. So in the mechanical properties, so how does it change if you mix your stainless steel with this other metal?
Yes, very good. So in terms, because I didn't show in the presentation, it was shown in the publications. Very clearly, we compare the tensile properties, the mechanical properties, the strength, which can reach about 500 megapascal, which is the same, very similar to the normal stainless steel. The elongation reduced a little, but it's still sufficient for any application. We can still go to beyond 30% of the tensile uniform elongation. So in this case, it's quite ductile, it's quite strong, like just you behave like a normal stainless steel. Of course, only one drawback. We do have drawback. The drawback is the reduce the corrosion resistance comparing to this 316L. So our corrosion resistance is also shown in the publication. It's actually similar to a 200 series of stainless steel, because 300 stainless steel has the best in terms of commercial, normal commercial available stainless steel is very good for corrosion resistance, but 200 is lower. But in our case, we test is similar to a 200 series of stainless steel. So that's really one of the drawbacks. Yeah.
Okay, that's good enough, I believe, because copper is known for this poor corrosion resistance. Another one is about this hazard to human body.
Yes, because I mean stainless steel is using copper. Copper has been used for many. I mean, even you have copper pots in the kitchen. Right. So I mean, you have stainless steel pots in the kitchen in your daily life. So we are not putting into as implants. We're not putting into your body. It's a surface contact. It's just a touching, like we do a stainless steel, let's say lift buttons and hand door handles, for instance. It's a touch, or maybe in the, I mean, just touching. So in this case, we don't worry about the harmful to the human, because copper, you feel it. I mean, you touch it, stainless steel, you touch it. So in this case, I don't worry. Yeah, thank you.
Okay, right. So there's another very detailed technical question, I think, for Shih-Chi. So how efficient or how energy efficient are DMD-based microscopes? What optimizations are in place to reduce energy usage, and what other possible optimizations could be made in order to improve energy efficiency?
Well, this question is not directly towards the material I presented, but the DMD microscope instead, one of our published work. I assume the person who asked the question have read the paper. So theoretically, the best efficiency is around 10%, but practically I think it's below 5% in terms of laser power efficiency. But these days, the laser systems are all high power. So, and for imaging, usually we need around only 50 milliwatt versus a 4-watt laser. So low efficiency at the present point is not limiting the performance of a DMD microscope. Yeah.
Okay, right. So I think I will turn to one more question for what was this question to? Okay, for Mingxin, and then we'll come back to some more general common questions. So the question to you is for your stainless steel, are they going to be rapidly applied in just rotations? That's one, and are your technology can be somehow applied to plastics using a similar? I'm not sure. I think he's asking, is there any technology that can be applied similar to your kind of results, but apply to plastic, not stainless steel?
Oh, okay. So yes, if not stainless steel, you can, if you use the other metals and alloys, I think as long as you have copper, enough copper. So for instance, you can use bronze, you can use other, let's say, high copper. I think the antivirus properties will be also there, not necessarily to be stainless steel. Because
but the question is asking to plastics. So not like plastic, yes. Right? Not metals.
So plastic, a polymer, I don't know how you put such a high copper content into a polymer base. If you are able to make this copper into a polymer base, let's say polymer base composite, for instance, you're using copper powders together with the composite in polymer. I guess so, could be possible, but we haven't tried.
I think it's quite possible. I mean, for example, in our group, we do a lot of copper fabrics, copper fibers, and textiles, and copper coatings on plastic. That's exactly what we do in the lab. And
yeah, in that case,
yeah. No problem.
Okay, so, in that case, adhesion and not leaking, not going out, and that could be a good way to try. That could be a good way to try.
So probably our stuff is also antivirus. I think that recall me. I actually wrote a proposal to ITF.
Okay.
Saying that our stuff is anti-COVID-19 and asked them to fund us. They didn't fund us. So from your result, it looks like our stuff should be naturally anti-COVID-19 yes. or whatever influenza. Actually, we quote, SARS-CoV-2 and the influenza in the study, but they didn't fund us. We don't know why.
You should get the real data. I mean, you're welcome to Hong Kong U and to do this real data, real testing. Yeah. Okay.
Yeah, I think I contacted Leo too. Leo was too busy. His lab is fully occupied. So yeah, we'll talk about that later. Sorry for interruption. Right. So let's go to some more general questions. I think about technology transfer, etc. and etc. There's also one question. I think asking all of us that related to nano fabrics or clothes. I don't know what does this refer to, right? And that's a question in Chinese is what estimation do you think that nano clothes or nano fabrics will be on the market? What's the bottleneck of this kind of technology? I think probably, I'm not sure. I'm not sure is the question related to Shih-Chi or because none of us here are doing actually nano coating for clothes, right? Even though I think we somehow understand a little bit of the common sense. So, but I think a related question to that is that how do we do the technology transfer? I think there are several questions actually related to this and how long does it take, for example, for us to do this kind of research to this stage? Looks like there are applications already being applied. Number two is that what's the biggest difficulties of finding, collaborators for commercialization or for production, etc. So maybe I think any of you can start to reply or comment.
Maybe I can do a quick here because our pattern has been applied and we shouldn't signing a let's say patent transfer to a company. We are on the way. Things should be quickly soon. It's one company interested using our technology to make their products. So the Hong Kong U is actually negotiate. I think soon that can be signed this one. So how to do? I think this really depends on my understanding is that the product has to be, if you want to be easy, quick to the industry, you should not change too much of the production line. That's my understanding. If you change a lot the production line, you take time, you need to educate the markets. The investors, the companies need to invest a lot of money to change the production line. So in our case, we're using existing production lines that's mature enough so that we just change the chemical composition of the alloy. So that's something I like to share. If you like to speed up, don't change too much the production lines. The supplying trends, if you change a lot of supply trends, I think this will be very low. That's my understanding. Yeah. Okay,
so not changing too much of existing technology or processing, right? But adding value.
Especially the processing, yeah.
Right. How about Shih-Chi? You are in a very different industry.
Well, I think in terms of technology transfer, there are usually two routes. One is, we can start our own spin-off company and seek, government supports in terms of funding and working with larger companies. And the alternative route is we have license, we have patents, and we are hoping larger companies will come and license the patent, and we assist them in commercializing the product. Yeah. So these are the often routes.
Right. I think I can supplement to that because we also have startup companies and we also find very difficult to commercialize our technology, our flexible batteries and then metallic fabrics. I think in Hong Kong in general, because the industry is quite specialized in certain directions, right? And so it's actually, and the production is not in Hong Kong, probably in some other cities close to Hong Kong or in other countries. So it's indeed, number one, it will be quite difficult for us as academics to talk to correct industrialists. And that's why I think having this YIC, Hong Kong ASK, this kind of joint workshops is very, very meaningful so that everybody can know each other, and then knowing the technology that we develop in the university and knowing the needs in the industry. So we can collaborate in the future to start with some collaboration and discussions. And I also agree that from Mingxin that if you want to commercialize something, you want to minimize the cost or the what would say the travel that from the industry, right? And then give them more added values. So I think from an academic point of view, sometimes we are a bit naive that we don't really know what's the pain point in the industry, right? Even though we think our technology is brilliant, we may sometimes be naive that we think this is what industry needs, but actually that's not what the industry needs. So then again, this joint forum will create opportunity for the industry to tell us what is necessary, what's their pain points, and so that some of us may fit in to solve your problem as well. So I think this is a bilateral or multilateral discussion is needed to have this sort of further moving towards the commercialization process. Now, let me see. I think there's more questions coming in while we are doing the discussion. I think most of the audience will be interested in, for example, our technology. How can we just lobby to the government, to our government, to have them apply in more like in a bigger scale, or how can the government help us apart from the industrialists to commercialize the technology? Anyone want to comment on that? Since now we are going to have a new government, right? And then Professor Sun Dong from CityU is going to be a leading person in this reindustrialization and then commercialization, innovation, technology. So
maybe I can just share what I have experienced when I was studying outside, and then I've seen. So if you look at Europe, there are many, let's say in Germany or in other countries, there are many PhD students are actually supported by the company, and also supported partially by the government. Look at the France and Germany, where there really heavy industry involved. So a PhD student maybe half is supported by the government and by the industry. And the universities, we do the research which relate to the industry, but it's not developing products. The university should not develop product for a specific company because we are using a taxpayer's money. But we are developing a fundamental understandings relate to the industry. For instance, a common knowledge that industry A and industry company A and company B both can use to develop further their products. And at the same time, we also train those students, which has an industry, because they also collaborate with the industries during the PhD. So after the graduation, these PhD students naturally, many of them are actually work in this company, in the R&D center of these companies. So basically, the company does not spend another 4 years to train a fresh graduate to be a sufficient engineer. So in this way, it's really a win-win situation. The company, if they also gain knowledge. At the same time, they already pre-screening, pre-training a very good engineers for their use. So in this case, what we can propose, maybe we can propose government doing something similar idea. So the government can propose this kind of a supporting for the PhD students or for the postdocs. Usually is the PhD students always the good case. In this way, the project is a very industry related. It's not only by the RGC type, purely fundamental research. So we need RGC fundamental, but in this ITC projects, this could be a very useful an idea. That means like we create two types of PhD students. One is working really in the industry related problems. Yeah, that would be my one of my suggestions if we like to propose.
Right, that's actually has been running a lot of very successfully in Europe. And it's quite unique in Europe, I would say, right? Especially in the European mainland, the continent,
yes.
not the UK.
Yeah,
right.
So my PhD was really like this way, and many of my friends are doing the same thing. So after they're working in the company for a few years, it's not necessarily like for myself. I work for the company a few years, and I feel I like to go to academy. You can change. So, but then in this case, I have really experience. I can speak the language as the industrial engineers we speak. So in this way, the collaboration between the university and the industry will be a lot easier, because as long as you speak the same language, in this way, same technology language, the collaboration will be a lot easier.
Right. I think this is quite a good way that the government and then the industry and the university can work together to think about that. Shih-Chi, do you have any comment? Because you are mostly from the US background, and you also work for a company, right? Or for companies before you become academic.
Right. I think in US, there's a specific grant category called a Small Business Innovation Grant. So that is actually for small companies to apply or jointly apply with universities. That's the STTR grant. So I think in US, many universities have already working with industries, but the school's fundamental purpose is to perform research. So by the end of a PhD or a project, it's usually just a prototype, and there's a big gap between real products. And at this point, many companies would hesitate to directly invest because it may take many years. So at this point, many small companies or startups or even middle-sized companies will apply for a Small Business Innovation Grant or SBIR grant for support. So each award is about $1 million US. And many middle-sized companies are actually surviving on these grants until their product become matured. And the definition of a small company is any company that less than 500 employees. I think in Hong Kong, that's not, really a small company anyway, with, engineers,
right,
staff of 500, right? So that, I think that really closed the gap between school prototypes and mature products. Yeah.
Right. May I know this 1 million, is it like upfront or is it a reimbursement-based type of grant?
It's upfront, but it's usually consists of 2 phases. So you apply for phase 1, so that's usually around 150,000 US dollar, but it's 6 months. But if you have more results, you can, directly apply for phase 1 and 2, and they will give you the money and you use them. It's not reimbursement based. Yeah. And so essentially they will give you money to, but it's essentially for, a gray area between product development and research. And they will not take companies' shares. It's just a government award. Yeah. As research.
I see. Yeah, I think in Hong Kong, we don't have this kind of award. It's more, for example, the science park or the biotech is more on the reimbursement base.
Right.
And then take the example that the company I get involved, the reimbursement started for example, like for postdoc or like human manpower reimbursement. It started once your company actually are in the science park, and then it only can be you can only start to apply it after you are actually there for a month.
Right.
And then it took a few months for the government to vet it. And after they granted your applications, then you probably wait another 6 months before you can apply for reimbursement. And the application for reimbursement will probably take another 1 to 3 months. So that means after you starting your company, you'll probably take 1 year before you can actually get any reimbursement of manpower. And manpower in Hong Kong as a startup probably is the biggest spend, right? So, so that means you need to have a lot of cash flow. That meaning like a few million actually, or 1 to 2 million Hong Kong dollar. But then what a startup company lacks is free money, right? So I think in that scenario, it would be quite great, all right? I wouldn't say good, but it's great if Hong Kong can also have this similar type of upfront grants for a startup or small scale company that can ease out lots of this kind of cash flow issues.
Right. I think from Zijian's point, that's totally correct. Reimbursement base is troublesome. But another point is you can only apply for this type of award one time, right? You cannot apply next year. And, it's usually applicable to new companies started within 2 years. And that's another issue, right? Because you can remain in a small R&D company form for several years. And to apply for the award, you may have to dissolve your company or restructure, which makes things more complicated. Yeah. Right.
Yeah. So I think that there's another question, probably a more general question about the pandemic. How does the pandemic affect our research progress? Is there any for example, machines, equipment, or our postdoc research scientists or engineers that probably cannot or arrive late in Hong Kong due to the pandemic?
Well, I think this is a major issue that needs to be immediately addressed by the government, because all the technical engineers overseas cannot come to Hong Kong to repair or install instruments. This is a huge issue. I think many universities, I think all schools are involved. They bought instruments to be installed, but their engineer cannot fly into Hong Kong for installation. Yeah, and sitting in the corridor or shelf for a long time. Yeah.
Now we have a machine which was in the order of 10 million, 20 million Hong Kong dollar machine, stay in the lab, ideal for 2 years without engineers coming. So if it's
the warranty already gone.
Of course, that will not start using, so the warranty is still there. But the things, if you discuss the loss in terms of the commercial way, let's say a rate every year, you have 10% loss, for instance. So you already lost a lot of money. Yeah, this is serious. And also, if it is broken, as Shih-Chi said, if the machine is broken, I mean, because usually Hong Kong has local support in the past years, because it's very convenient for engineers coming from Singapore, from mainland, from Taiwan, and it's very easy. The engineers can easily travel to Hong Kong, but now the pandemic is no. So my personal lab are actually affected seriously due to this lack of local engineers. Yeah.
Right. I see Anderson turn on his camera, so probably he wants to supplement on this.
Not really, but I just like to concur that indeed I think it's a huge issue, and it's becoming bigger and bigger of an issue. And I think this raises, besides the problem of border being open or not, whether engineers and people can come in to install and do the training. Another problem that may be equally, if not more important, is that do we have enough local talents to build and maintain and even or just install equipment? And if we continue to grow in our investments in research in these areas, it may be worthwhile for us to also groom our local talents, not only in conducting research projects, but also in designing, in building, and also maintaining our equipment. So maybe something worthwhile to think about as well.
Well, I think it's the entire ecosystem, right? from the first start to the end. And the problem in Hong Kong probably is because of the unhealthy ecosystem. We've got a very strong R&D in the institution, but then in the front and at the back is something missing. So then the chain doesn't go gear up very smoothly. And I think that I think we don't have I don't receive new questions, and then the time is almost there. So Anderson, would you like to wrap up a little bit before we end this in the workshop?
Sure. So first of all, thank you, Zijian, for leading the section. And thanks very much to Shih-Chi and Mingxin for sharing with us some of the really exciting works. And these works not only have scientific significance, but also have very strong applications and practical relevance. So we hope that more of our research can be geared towards this direction, and these provide platforms for collaborations between scientists and industrialists to really realize the impact of our research for Hong Kong and for the innovation and technology ecosystems that Zijian also mentioned in Hong Kong, Greater Bay Area, to benefit China and beyond. And with that, I'd like to thank all of you for attending. And it's been great to partner with the Hong Kong Young Industrialist Councils. And we hope that we'll bring to you more of these kind of workshops. Please stay tuned. Our Young Academy of Sciences have a lot of activities. Please follow our website, our Facebook, and also our Instagram. You will see a lot of the announcements of our activities. Thank you very much.
Thank you, Anderson. I also would like to thank the organizing team, Ada, Oscar, and everybody to organize this wonderful event. And thank Shih-Chi and Mingxin for giving the nice talk. So for anyone, the public and the industrialists, if you would like to know more, or you can just personally contact us, or you can send your questions or any requests to our Young Academies of Sciences, and we will do our very best to come back to you shortly. Okay, so I think without further ado, I will say this is the end of today's industrial workshop, and I hope to see you guys either online or face-to-face in the near future. Thank you very much.
Thank you. Bye-bye.
Bye-bye, everyone.
Bye, everybody.